All right, let's dive deep because today we're heading straight into the engine room of modern AI. You've seen the incredible stuff these big generative models can do, the images, the text. It almost feels like magic,
It really does.
but actually engineering that magic, well, that's a whole different ballgame.
Hmm.
And one of the biggest challenges right now, maybe the biggest, is designing the architecture, the actual structure of these huge neural networks. How do you even figure out the best way to build them?
Yeah, that's the core question.
Our source material today is this really fascinating new paper that tackles exactly this. It asks a pretty fundamental question. If you're dealing with models that cost, what, millions to train,
Often, yes, millions.
how on earth do you experiment with new architectural ideas? Because typically trying a new design means you have to start all over again, right? From scratch.
Exactly. And starting from scratch with today's foundation models, these enormous ones, it's just prohibitively expensive.
Prohibitively.
We're talking massive amounts of compute, huge amounts of time. The paper uses a great analogy. It's like trying to test if a new window design works better for a skyscraper by tearing the whole building down and rebuilding it every single time you have an idea. Wow. Okay.
That's the scale we're talking about. The sheer cost just slams the brakes on iterative architectural design. It's almost impossible.
So the structure, the architecture itself is super important, but messing with it is locked behind this huge cost barrier.
Precisely.
So the paper's big idea, and I guess our mission today is to figure out, is there a shortcut? Can we actually explore and, optimize the architectures of these giant pre-trained models without footing that multi-million dollar retraining bill every time? Can we innovate on the structure?
Yeah, like how software developers build new features onto existing code instead of rewriting everything.
That's exactly the problem this paper introduces grafting to solve.
Grafting, okay.
Grafting is presented as this innovative, cost-effective method specifically for doing that iterative architectural exploration. Optimizing large generative models. It's all about enabling what they call architectural editing directly on models that are already trained, already powerful, but doing it under small compute budgets.
Okay, architectural editing, let's unpack that a bit. The paper really emphasizes how hard it is right now to get insights into what architectures actually work best. It's not just the data, not just the algorithms, that the actual structure is critical, but it's just so expensive to experiment with.
Exactly right, especially for these foundation models, and particularly the generative ones like diffusion transformers or DiTs. These are the engines behind a lot of state-of-the-art image and video generation.
Right.
For those, if you want to make a significant architectural change, the standard approach is training from zero, and that approach just doesn't work for rapid exploration. You can't run tens or hundreds of experiments if each one breaks the bank and takes months.
Okay, so if you can't afford to rebuild the whole skyscraper every time, how does grafting let you, like, swap out the window frame or maybe reinforce a wall?
Well, it proposes this really clever two-stage approach to do this architectural editing. The core idea is you directly modify the computational graph of a model that's already been pre-trained.
The working one.
The working expensive one, yes. And you strategically swap out components or maybe add new ones to try out your new architectural idea.
So, like, taking out one type of layer and putting in another.
Exactly. For instance, you might replace a standard multi-head attention layer, an MHA layer, with something different, maybe a convolutional operator or perhaps a more efficient type of attention mechanism.
Okay.
But, and this is the crucial part, you can't just drop a randomly initialized new piece into a complex, highly tuned network.
Right. That sounds like a recipe for disaster.
It is. It's like trying to jam a random brick into a finished Jenga tower. The whole thing just collapses. So grafting needs two key stages to make that swap work smoothly.
Okay, that makes sense. You can't just yank something out and shove something random in its place. So, what's stage one?
Stage one is called activation distillation.
Activation distillation.
Yeah. The main goal here is to get the new operator properly initialized before you actually integrate it into the big pre-trained model.
How do they do that?
They frame it quite elegantly, actually, as a regression task. You take the new untrained operator and you feed it the same input that the original operator, the one you're replacing, would normally see in the pre-trained model.
Okay.
Then you train this new operator to predict the output that the original operator produced for that same input.
Ah, okay. So you're basically teaching the new component to act just like the old one it's replacing, using the old one's behavior as the target.
Precisely. You're distilling the function, the sort of knowledge, from the original operator into the new one. But you're doing it in isolation and, crucially, using limited data.
How limited?
The paper found you can often get a surprisingly good initialization with very few samples. Sometimes as few as like 8,000 examples might be enough for a single operator.
Wow, 8,000. That's tiny compared to pre-training datasets.
Exactly. It's conceptually related to Hinton's classic work on knowledge distillation, but applied here at this really granular level, component by component.
And they looked into the details here, like the loss function for this teaching process, L1, L2, Huber loss. Does that choice actually matter much?
Oh, it absolutely does. And this is one of the really neat technical insights from the paper. They dive into this in their analysis, things like Table 1 and Figure B.2. They found that inside these big models, especially deeper in DIT networks, the activation values can vary wildly. There's significant variance. Okay, so if you just use a standard L2 loss, which squares the error, it gets really thrown off by large outlier activation values. It makes it hard for the new operator to accurately mimic the original one's typical behavior.
Because it focuses too much on those huge, rare values.
Exactly. So they found the best objective actually depends on what you're replacing. For MHAs, which showed this high activation variance, L1 loss worked better. It's less sensitive to outliers.
Right, absolute difference, not squared.
Correct. But for MLPs, which seem to have less extreme values, standard L2 was actually fine.
Interesting.
It shows that getting that high quality initialization in stage 1 isn't just plug and play. You need to understand the statistics of what you're trying to mimic and choose the right tool for the job. That tailored approach is really key for the swap to work well later.
Okay, so stage one gets the new piece ready by having it mimic the old one using minimal data and a smart choice of objective function. But what if you're replacing lots of operators throughout the network? Doesn't the error, even if small for each one, kind of add up?
That is exactly the problem stage 2 is designed to fix. It's called lightweight fine-tuning.
Lightweight fine-tuning makes sense.
Yeah, the paper explains that when you integrate multiple of these newly initialized operators, even if they're good mimics, those small approximation errors can compound. They can propagate through the network and ultimately degrade the overall performance of the model.
So you need a cleanup step.
Basically, yes, stage 2 mitigates this. You fine-tune the entire model, the one with all the grafted pieces in it, end to end. But the critical part is you do this using a relatively small subset of the original training data.
How small are we talking about for the data? Still much less than full pre-training.
Oh, much less. This was another really significant finding which they show in Table 2. They discovered that even after replacing all the MHA layers or all the MLP layers in a big model like DiT-XL2,
Replaces all of them.
yes, all of them, they could recover competitive performance using surprisingly small amounts of data for this fine-tuning stage. Often just 10% of the full original training data set was enough to kind of iron out those accumulated errors and get the quality back up.
10%. That's remarkable.
It really is. They showed clear benefits going from tiny amounts, like less than 1%, up to that 10% mark. And this low data requirement is absolutely fundamental to why grafting is so cost effective.
So quick recap. Stage one initializes the replacement locally with minimal data. Stage two cleans up the whole network with a bit more, but still limited, data. How did they actually prove this two-stage dance work, that it can recover performance before even trying wild new architectural ideas?
That's a great question. They ran a really important control experiment. It's detailed in section 3.2 and shown in table 2. They called it self-grafting.
Self-grafting.
Yeah, the idea is pretty simple. They take an operator, let's say an MHA layer in the pre-trained model. Then they use the grafting procedure, both stages, to replace it with a new, randomly initialized MHA operator, the exact same type of operator.
Ah, so the architecture doesn't actually change at all.
Correct. They're just using grafting to swap out a piece for another identical piece, just starting from a random initialization for the new one.
Okay, and what does that tell them?
It acts as a crucial baseline. It validates the grafting procedure itself. If grafting can successfully replace an operator with an identical twin, essentially, and recover the model's performance using only limited data.
Then the method works. The two stages are doing their job of integrating new components without wrecking the whole thing.
Exactly. It isolates the effectiveness of the grafting process and also lets them study things like how much fine-tuning data you need for recovery. The fact that self-grafting on a big model like DiT-XL2 got back to near baseline performance using just that 10% data really validates the core methodology.
Okay, here's where, for me, it gets really, really interesting and maybe a bit counterintuitive. Before they even started grafting in new types of operators, they did some analysis on the original pre-trained model. Specifically on those multi-head attention layers, they used something called the band K metric, section 3.4, figure 2. What did they find out about how MHAs actually behave?
This was, I think, a genuinely surprising and really impactful finding in the paper. Multi-head attention, theoretically, is designed so that every element, every token in a sequence can attend to every other token. It has this global receptive field capability.
Right, that's its whole point, isn't it? Global context.
That's the theory. But their analysis using this band K metric, which basically measures how much of the attention weight concentrates within a certain local window or band around each token, it revealed something unexpected. In the pre-trained DiTs-XL2 model they studied, the MHAs were actually behaving in a largely local manner.
Local, but they're designed to be global. How local?
Yeah. Figure 2 in the paper really visualizes this well. On average, a big chunk of the attention mass, the actual weights, was focused within a pretty narrow window right around the token itself.
Huh.
In many layers, for instance, more than half the attention weight fell within a band of just 32 tokens nearby. It was really only the very early layers in the network that showed more strongly non-local, more global patterns.
So the deeper layers are mostly looking nearby.
It suggests that, yeah, it implies that maybe the deeper layers are relying more on local context that's been aggregated and passed up from the layers below, rather than constantly doing truly global computations themselves. It kind of challenges the standard intuition about how MHA is used throughout these deep networks.
Okay, wow. And why is finding that out that MHs are acting locally anyway? Why is that so incredibly useful for this whole architectural editing idea?
Because it gives you a principled guide for replacement. It's huge.
How so?
Well, if you know that a specific MHA layer in your expensive pre-trained model is mostly just doing local computations anyway, even though it could look globally.
Then maybe you don't need that expensive global capability there.
Exactly. You have a strong hint that you might be able to replace it with a different operator that is designed to be local and is perhaps much more computationally efficient, like a convolution or some form of local attention mechanism. And you might be able to do that without seriously hurting the model's performance.
Right.
It turns architectural editing from just blind guesswork or trying everything into a much more informed, data-driven process. You're guided by how the pre-trained model is actually using its parts.
That's really cool. Okay, so armed with this insight, MHA is often local. They then introduced some new operators designed to be efficient local alternatives, right? Which ones did they experiment with using grafting?
Right, they proposed and tested operators called Hyena X and Hyena Y. These are described as efficient gated convolution operators. They're specifically designed as sort of drop-in replacements for MHA that leverage that locality finding.
And they're more efficient.
Yes, particularly they scale much better with the length of the input sequence compared to standard MHA, which gets quadratically expensive. They also included other efficient options in their experiments. Table 3 lists them things like different kinds of local attention and even efficient MLP replacements.
Okay, so they grafted these potentially more efficient, often local operators into the pre-trained model. What did the results show? Table 4, I think.
Yeah, Table 4 has a lot of the core results. And one of the main takeaways the paper highlights, they call it Takeaway 1, is the, quote, surprising effectiveness of operators with smaller receptive fields under interleaved grafting.
Okay, what does that mean in play English?
It means that these efficient operators like FWA, sliding window attention, and their hyena variants, which are intentionally designed with limited local receptive fields, they actually performed remarkably well when grafted in to replace the MHAs.
How well?
They achieved image generation quality scores, FID scores, that were very close to the original baseline model that used the full expensive MHAs. It strongly validates that grafting, when guided by insights like MHA locality, can successfully transition these big models to more efficient architectures without a huge performance hit.
And it wasn't just what you replaced the layers with, but where you put the replacements, right? The strategy mattered.
Absolutely, that's what the interleave grafting part refers to, and Figure 4b illustrates it. They found that just replacing, say, all the MHA layers in the top half of the network where they found more locality wasn't always optimal.
Why not?
It seems that an interleaved strategy often worked better. That means swapping in the new operators in a pattern across different depths, maybe alternating between the original MHA and the new efficient operator every few layers.
Ah, like mixing them up.
Exactly. It suggests that maintaining a kind of hybrid architecture where you distribute the different computational strengths across the network might be really important for preserving the overall performance after you've done the grafting.
Okay, so they showed it works on these standard benchmarks, but then they really pushed it, right? They applied grafting to a much tougher, more practical problem, generating really high-resolution images, 2048 by 2048 pixels from text descriptions using a model called PixArt-Sigma.
Yes, Section 5 covers this. And this is a seriously challenging setting.
Why so challenging?
Well, first, generating images at that resolution means the internal sequences, the model processes, become incredibly long. We're talking 16,384 tokens. Standard attention mechanisms really struggle with that length.
Okay, yeah, that quadratic scaling bites hard there.
It does. Plus, you have the complexity of conditioning on text input. It's multimodal. And then there's a very practical problem. There isn't much large-scale public training data available at that super high resolution. So for the fine-tuning stage of grasping, they had to rely on more limited or even synthetically generated data.
Right. But the goal was still to maintain that high quality generation like the examples they showed.
Exactly. Figures 1C, 1D, D.2 show the kind of impressive image quality they were aiming to preserve while making the model faster.
And was MHA the main bottleneck here again, like the locality analysis hinted it might be in long sequences?
It absolutely was. The paper points out that in this high-res PixArt's model, the MHA operations were responsible for over 62% of the time it took to generate an image. 62%.
Wow, so they were the obvious target for replacement using grafting.
The prime target, yeah.
So what happened? What was the payoff for applying grafting in this demanding real-world scenario? Did they get a speed up?
They did. This is result 2 in the paper. Using only 12,000 synthetic data samples for that lightweight fine-tuning step, remember. Very limited data.
Yeah,
Their grafted PixArt's model achieved a really significant speedup. It was 1.43 times faster at generating those high-res images.
almost 50% faster.
Pretty much. And critically, this came with only a very small drop in the generated image quality, measured by a metric called Niebles score. It went from about 49.75 down to 47.78, a tiny dip for a big speed game.
That's a huge practical win. It shows grafting isn't just theoretical, it delivers real efficiency in complex modern AI systems.
Exactly. It's a very strong demonstration of practical utility.
They even took it a step further than just swapping operator types. They used grafting to actually restructure the model's architecture, looking at a depth versus width trade-off, table 6. How did grafting enable that?
Right, this is the takeaway 3, and it really shows the flexibility of the grafting approach. They took a deep model, the DiT-XL2, with 28 layers,
Okay.
and they used grafting to essentially convert pairs of sequential transformer blocks one block after another into parallel blocks, working side by side.
So instead of going deeper, they went wider at certain points.
Effectively, yes, this restructured model ended up having only half the depth, just 14 layers, but was wider or had parallel paths. The key thing is that grafting provided the methodology to actually initialize and fine-tune this radical restructured architecture successfully.
And what's the benefit of making it shallower like that?
Speed. They achieved a 2x speedup compared to the original deep 28-layer model.
Twice as fast.
Twice as fast, while maintaining comparable image generation quality. You can see some examples in figure C.1 in the appendix.
That's impressive.
It really highlights that grafting isn't just limited to swapping, say, an MHA for a convolution. It can actually facilitate more fundamental architectural changes, like manipulating depth and width, which can have major implications for entrance speed and latency.
It sounds incredibly powerful, really flexible. But, good research is usually honest about limitations. Did the paper acknowledge any downsides or areas where grafting maybe didn't work perfectly?
Yes, absolutely. Responsible work always does. They mention, for instance, that in some of the experiments, particularly those relying on synthetic data for the fine-tuning,
Like the high res one?
exactly, the quality of that synthetic data might have limited the results sometimes. They show some examples of failure cases or suboptimal outcomes in the appendix, figures D.3, D.4, and suggest data quality could be a factor.
Okay.
So it's a good reminder that even with a clever technique like grafting, the data you use in that lightweight fine-tuning phase still matters. Garbage in, potentially less than perfect out.
Right. So, okay, zooming out from the technical details, what's the really big picture here? What's the core contribution of grafting for the whole field of AI R&D?
I think the core innovation is that grafting offers a genuinely accessible and much more efficient way to do architectural exploration and optimization, specifically for these massive pre-trained foundation models. It effectively dismantles that huge multi-million-dollar barrier of having to retrain from scratch every single time you want to try a new architectural idea.
Which means,
Which means architectural experimentation becomes feasible for way more people, for researchers, for developers, for labs that don't have access to, hyperscale compute resources on tap.
so connecting this back to you, the listener listening right now, this could seriously speed up progress in AI, couldn't it? If architectural innovation isn't just confined to a few giant tech labs anymore.
Exactly. Grafting could help democratize that process. It allows for much faster iteration, more experimentation, maybe more tailoring of model architectures for specific needs.
It's like bringing that agile, iterative development cycle we see in software, bringing that to the actual structure of the AI model itself.
That's a great way to put it. It provides a practical methodology for architectural editing of large foundation models. And that's fundamentally a new capability compared to the old way, which was basically train from scratch or don't touch the architecture.
Right.
And the paper even points towards exciting future directions, things beyond what they tested correctly, like using grafting to adapt models specifically for super high-res tasks, or to handle really long video sequences more efficiently, or maybe building faster, more responsive models for interactive AI tools where latency is critical.
Okay, so let's try and recap the core of this deep dive then. Grafting is this innovative two-stage process. Stage one, activation distillation, which initializes new or replacement operators by teaching them to mimic the original ones using limited data.
Right, and using carefully chosen objectives.
And stage two, lightweight fine-tuning using another small slice of data to smooth out the integration of these new pieces across the whole pre-trained network.
Correct.
And this whole process allows for cost-effective architectural editing of these giant, expensive models. We saw how key insights like discovering that MHAs often act locally in DiTs can guide which operators you might want to swap out.
Leading to potentially more efficient hybrid architectures.
And it can even enable bigger structural changes like that depth to width trade-off, giving significant speedups, all achieved much, much faster and cheaper than retraining from scratch.
It really is a significant step forward. It makes architectural exploration a much more agile, dynamic, and frankly democratic process in this era of enormous models.
Which leaves us and you with a final thought to maybe chew on. If that massive cost of retraining from scratch is no longer the main roadblock to exploring new AI architectures, what happens next?
Hmm.
Does this grafting approach lead to, say, an explosion of highly specialized, super efficient models designed just for narrow tasks? Or could it actually accelerate the discovery of fundamentally new architectural designs, new paradigms we haven't even thought of yet?
Yeah, what new possibilities really open up when iterating on the very structure of these powerful models becomes almost as common as, I don't know, updating an app on your phone?